Hi. Hmm. Hi, can you hear me? Hello? Okay, now welcome to the, oh, sorry, maybe it's the online tutorial 3. And I'm Yuhao Wu. Yeah. And today's online tutorial is about some important concept in the maximum likelihood function and the relevant assumption with maximum likelihood function. And something about the robustness. And the robustness is about the robustness of surrogate loss function. Okay, and we will use some intuition examples like some true case and with some coding to help us to have a very deep understanding about the maximum likelihood function. Okay, maybe I will cover this content in 1 hour, and we have another 1 hour for Q&A, and you can ask any question about this online tutorial content. Okay. Uh, Now let's get started about today's online tutorial. Okay, the first thing is like the maximum likelihood function. Before we go into the maximum likelihood function, the first thing is we want to know what is a likelihood function. We have a very clear definition about the likelihood function. The likelihood function quantify how probable it is to observe the given data for different values for the model parameters. So the important things, there are three important things. One is probability. Another is observed given data, like some training data or observed samples, and the model parameters. This means you need to use some observed training data and to measure the probability of this training data with different model parameters. Okay, so intuition, you tell us which parameter value make the observed data most likely under the assumed statistic model. Okay. Uh, Now we can go through one intuition examples. Just a very simple example about a weight of a mastery object. Image in this case, sorry. Okay, imagine we are trying to determine the weight of an object using a factor scale, and this scale cannot return the exact weight. But
18-year-old having a baby. Oh my. She's 18, same age as me, and she's got a kid.
sorry, Josie.
She has a baby.
Oh, can you mute yourself, firstly?
That's common.
Now we have a scale, and we want to use this scale to weight an object. But this scale cannot give an exactly weight. But there varies around the true weight due to some measurement errors.
I want another sausage with sausage. I want
Right,
another
Josie?
sausage. When you leave, let me know. Okay. 2 minutes late.
Okay, now we have a scenario like we weight an object multiple times and get a different reading in our scale each time due to different errors. And for example, if we get the three measures, uh 9.8, 10.2, and 10 kilo, this is like the different reading in your scale, and you want to use this measurement to estimate what is the true weight of this object. Okay, because you do not know the actual weight of this object. Okay, so we were going to use the maximum likelihood function to estimate the true weight of this object. Okay. So we know for the likelihood function, we need assuming a statistical model. So normally we will assuming our have a Gaussian distributed model. For example, we can assume each of the measure x is modeled at equal to the theta plus epsilon I. This epsilon is like the error items. So these error times can cover some underlying factors which cannot be measured.
That's right.
Okay. Okay. Uh, okay. So the first step is like we assuming a statistical model. We assuming our x is equal to the true weight plus some error items, and we assume these error times is belong to a normal distribution with zero mean and sigma is the variance. Okay, this is the assumption. Based on this assumption, we can know like our x with the condition of theta is also belong to the normal distribution. So why, and maybe someone have issue about this connection. Why we make assumption like the error is belong to the normal distribution, why the x with the condition of theta is also from the normal distribution. We will going through this part in a later section. Okay. So now we have assuming a statistical model, our x with the condition of theta. This theta is the true weight. It also belong to the normal distribution. And the normal distribution, the mean is a theta. And the variance is a sigma. Okay. Now we want to calculate the likelihood for different guess of theta. Because we do not know what is true theta, maybe you can make some guess like the theta is equal to 9 kilo or equal to 10 kilo or equal to 12 kilo. And for different theta, different guess of theta with our training data or observed x value, we can calculate the probability. And this probability is the likelihood. Because we make assumption like the x is belong to the normal distribution, so we can use the PDF, the probability density function from the normal distribution. So this is a normal distribution probability density function. And we can just input this true value. Like, because for previously we have 3 observation of x. It's like a 6.8, 10.2, and 10 kilo. And for example, if we guess the theta can be 9.9 kilo, and we can calculate all the probability through the normal distribution probability density function. Okay, so for example, the first one, this is if the true weight is 99 and the x is 19.8, so the likelihood about this one is this value. It's a value. Okay. So for this item, actually we calculate how probability if we have observed x equal to 99.8 kilo and the true weight is equal to 9.9. So we measure this probability. Okay. And we have different observation. We have 3 observation. So we can calculate all the event happen. So it's a product. This we also assume the measurement are independent. So the total likelihood about our observed data is a product of different individual likelihood, like here. So based on this formula, we can calculate the likelihood about the true value is equal to 99. Okay. Because for this one, we just make a guess about the theta, and then we guess the theta is about 99. Actually, we can guess the theta belong to any value. So for any value, we can also use three observation to calculate the totally likelihood and to write a plot like here. We have different guess about theta from 19.8 to 10.4, and we can calculate the likelihood about this different value about theta based on our observation, based on our three observation. So this is the likelihood. And because we assume the x is belong to a normal distribution, so we can direct calculate the likelihood function, and this distribution also is look like the normal distribution. And if we use like the maximum likelihood function, so the principle is like we want to choose the value which can return the maximum likelihood. So based on this plot, maybe you can find this is maximum likelihood. And maybe you can choose the theta is equal to 10. The 10, maybe it's a best estimation about a true weight. So this is a very intuition example about the maximum likelihood, and we use a very simple examples like to weight object, and our scale will return just some different measurement, and we use the measurement to measure which value have a maximum likelihood and which value is the best approximation about the true weight. Okay, and for this part, I can show you some coding. Okay, yeah. So anyone can show the coding, can see the coding. Okay, for this one, this is a coding like for the first case. For example, this one is our observed data x1, x2, x3, and we can use based on this value, we can calculate the sigma like this is standard deviation about this three value. Okay, and we want to have some different guess about the true weight. So we use this function, the numpy, to generate different guess from the 90.5 to 10. Like this different guess value. And we use this different guess value, theta value. And for each theta value, we use our measurement, this is our training data, and with a sigma to calculate the likelihood. Okay, and then we combine all the likelihood and to make a plot like here. Okay, so this is a final result, and use the maximum likelihood function. We will choose the value which can give the maximum likelihood. So we think the best approximation about the theta is a 10. Okay, so based on this measurement and based on our maximum likelihood function, we think the true weight is 10. Okay, so this is a very intuition example. And we're going back to our, yeah, we're going back to our textbook. Okay. Now we can give you another example about the maximum likelihood. This is about the linear regression. Okay, we already know for linear regression, we have an independent variable and a dependent variable y, independent variable x. Okay, in this one, we have a very simple probability problem. In this case, maybe I'm a teacher aiming to understanding the relationship between the number of hours students spend on studying and their test score. So maybe we can have that the more study time result in better test score. This means the positive relationship between the studying times and the test score. And we want to quantify this relationship using linear regression. Okay. So okay, if we want to use the maximum likelihood function, the first thing is use we assume we have a linear regression about this variable. And we also assume the epsilon is a normal distributed with the zero mean and the variance. For example, this is our estimation model. We think our starting hours and the test score is from a linear regression. Okay. And the beta 0 and beta 1 is the two parameters in this linear regression, and the epsilon covers some on measurement factors. Okay. It's a random error at term. Okay. So for this beta 0, this is like the intercept. It's representing the score a student will not study anymore, like the x equals 0. And the beta 1 is a slope, indicating that if we increase 1 unit of studying, how much we will increase the test score. So this is a real world meaning about this linear regression function. Okay. Okay, for linear regression function, the all processes same as the previous example. First, we're assuming the epsilon is belong to the normal distribution, and our y is also belong to a normal distribution with a different mean. Okay, this is like the assumption. This means for a given x, the y also follow a normal distribution central around the beta 0 plus beta 1 multiple x. Okay. And for this one, because we have already know some training data about x and y, so we can directly calculate the likelihood function through our probability density function. Okay. This is a normal probability density function. If we make an assumption like the Laplace distribution, maybe the probability density function is different. Okay. And because in our data set, the x and y, the observation about x and y, we have multiple x and y, so we need to calculate the combined probability. So we use the product to brought out the probability. But in the mathematics, we want to simplify the calculation, so we add the log items before. So we transform this equation into the log likelihood. Okay. And for the linear regression, we always use like the optimization method. It means to maximize the likelihood. Okay. So we will maximize this low likelihood because it has a negative. So maximize this likelihood is same as minimize the distance between the y and the beta 1 plus the beta 0 plus beta 1 x. Okay, so this also excites the ordinary least square laws do. Okay, and we also can write this function based on some observed data, like here, with respect to the beta 1. For this one, we just write a plot with respect to beta 1. Okay, and we will choose the local likelihood, which given the maximum likelihood. Maybe we'll choose like the 5 as the best approximation about our beta 1 because we chose the maximum likelihood. Okay. Now I will also give you the relevant coding. Okay, right here. Uh, this is a coding about our linear regression maximum likelihood function used on a linear regression. For this one, this is like the true parameters we want to estimation. We think the true beta 0 is equal to the 50 and the true beta 1 is equal to 5. and the sigma is 5. Okay. Based on these two parameters, we can generate our training data like here. They'll maybe have a positive relationship between the study hours and the test score. Okay. So now we have to use this training data to make our linear regression based on maximum likelihood estimation. Okay. So this is the whole coding about the maximum likelihood function. This one with the definition of function about the log likelihood. So this function is from the log likelihood function. And because in the optimization, we often want to minimize something. So we add the negative sign before the log likelihood function. So this we can tell this is a negative log likelihood function. So this is just for easy to make the optimization in computer. Okay. And then we will initial guess for these parameters. We will guess the beta 0 and beta 1 is 40 and beta 0 is 4. And the sigma is 10. Sigma is variance about epsilon. Okay, and we will minimize this negative log likelihood with given initial parameters. And we want to minimize this loss and return the estimation value. Okay, so this may be our estimation value. And for this bound, this function is just about to setting a boundary in your estimation parameters. For this one, because for the sigma is also greater than the 0, so we just make a constraint about the sigma. The low bound is a very little value. Okay, and we put this bound in the minimize optimization. Okay, and based on our training data before, we make a assumption, we make a estimation about our linear regression. Okay, so this is the result, beta 0, beta 1. And the ground truth beta 0 and beta 1 is 50 and 5. So the estimation value is very close, right? Okay, and we can also visualize this likelihood function, like here, for respect to the slope beta 1. Okay, so this is the slope beta 1, and then we have a log likelihood, and then we can write this log likelihood with respect to different value about beta 1, different guess about the beta 1, and to find which one have written the maximum likelihood, log likelihood. And choose this one is our best approximation. Okay. This is also a visualization about our estimate linear regression. And this linear regression maybe can have a good fitness about our training data. Okay. And for this one, it's like the measurement we use compare. It's like the compare about the yeah. For this one, we just show with the least square loss and the maximum likelihood function. This is very similar things. Okay, we use the least square loss here. Because for linear regression, we can take a derivation and direct calculate which value equal to the estimation. And for this one, we use the approximation. We use the minimize this value. So actually, these two things return the same value. Okay, we can see. Okay, so this is the coding about the linear regression, about the maximum likelihood function on linear regression. Okay, and we're going to our next. Okay, until now we have already know what is the maximum likelihood and what is the intuition example about the maximum likelihood function based on different case, like the weight of the object and the linear regression model. Okay, and now we have already note that in like here, we make assumption like our epsilon is belong to a normal distribution. With this assumption, we also think the x is also belong to a normal distribution. In another example, like the linear regression, we think the epsilon is belong to the normal distribution, but we also think the y is also belong to a normal distribution. So why we need to make this like the following assumption? We assumption the epsilon, we also assumption the y is belong to a normal distribution. Now we will introduce this point. Okay, why we assume like the y following Gauss distribution based on our assumption on the epsilon. Okay, for example, if we have a ground truth model in linear regression, our beta 0 and beta 1 is optimal parameters. So the beta 0 star plus beta 1 star and multiple the x is like the deterministic function. So you input one value and return one specific value. So if you make assumption about epsilon and this ground truth model is all optimal, and so this y is also belong to the normal distribution because this is a deterministic function. So you input value and will return a different value. It will return one specific value. So if this epsilon is belong to normal distribution, the y is also belong to normal distribution in the ground truth situation. So when we do the linear regression, we also want to optimize our model in a optimization situation like the ideal situation. So in this situation, if the epsilon is belong to a normal distribution, the y is also belong to normal distribution. So this is why we can falsely make assumption on epsilon, and then we also make an assumption on the y, and think the y is also from normal distribution. Because in the ideal or in the optimal situation, these two things is also all from the normal distribution. Okay, so we can make this assumption and to optimize this model. And our target is very great. Okay. And for assuming the normal distribution values, the process, we will review the process, like the assumption in linear regression. For since we assume the epsilon is belong to a normal distribution, and we will think this arrow is from normal distribution, and we will think the y is also from normal distribution based on different mean. And this mean is like the optimal parameters with x. Okay, so this is like the formula about the intuition about why we need to assume the y with the condition of x and theta follow a Gaussian distribution, because we think in the optimal situation, the y is equal to Gaussian distribution. So we can make an assumption falsely, because this y is the same as epsilon from the same distribution. Okay, so this is like the explanation about these things. And the last part is about the robustness of the surrogate loss function. because for this part, we just analyze the robustness of different loss function. So for this one definition, the robustness of loss function refers to how much the loss changes when the residual changes. The residual is a difference between the y and the prediction y. Okay. So how to measure the change because the residual change? How to calculate like the change ratio between the loss and the residual? Normally we will use a differential. Okay. We use a differential our loss function with respect to r. For example, in our tutorial slide, we have like the 1, 2, 3, 4. We have 4 different loss, and this loss have different loss function. For example, for the less square loss function, if we just input the r in this loss function, so this function equal to r squared. If we differential this loss function with respect to the residual r, we get the 2 multiple r. Okay, we can say if the residual is too big, the change rate is also very big. So this means less square loss compared to the another loss function, less square loss maybe it's not very robustness because a large residual can lead to the very large change in this loss value. Make our training model well sensitive to outliers. Okay, we can say like the Cauchy loss. This is a Cauchy loss function. And we also take a derivation with respect to r, and this is our function. We can see this function is slower than the less square loss. So this means the change rate about the Cauchy loss is slower than the less square loss. Okay, so maybe the Cauchy loss is, have a better performance on robustness than the less square loss. The second is the absolute loss. For absolute loss, if we take a derivation with respect to r, the value is just equal to the sign of r. So the value is just +1 or 0, 1. It's just a +1, it's just a +1 or -1. So this do not have any connection with the value about r. So the absolute loss have a better robustness than the less square loss. Your less square loss with r increase, like the large residual, the change ratio is also very large. But for the absolute loss, the change ratio do not have any connection about the value about r. So the absolute loss is more robust to the less square loss. Okay, and the second is called entropy loss. This is called entropy loss function, and we also take a derivation. And this alpha is just like the scale parameters. Okay. For large residuals, the change in based on this function, the change in the loss is also smaller than the length square loss. Okay. So based on this different loss function and take a derivation with respect to r, we can return to the different formula, and this different formula give me some insight about the robustness about different loss function. So we can say that compared to this loss function, the less square loss maybe it's not very robustness. It's sensitive to the outliers with increasing about r. Okay, so loss value will change very quickly with the large of the residual. Okay, So maybe in some case, if you want to have the more robustness in your model training, you may control like Cauchy loss or absolute loss. But another things you need to care about is like for some loss like the Cauchy loss, maybe they are not convex. So this is like a trade-off about the better optimization performance and the robustness. So maybe you can choose a different loss in your different training scenario. Okay, now we will also introduce some coding about the robustness on loss function. Okay, come out to the robustness of linear regression model. On noisy data, use different loss variable. On this coding, we just compare the L1 loss function and L2 loss function. It's an absolute loss and less square loss. Okay. The first thing is just loading some data from the website. Okay, this is our loading data. We have like the independent variable is budget and dependent variable is sales. So this is like X and Y. This is our given data set. And for this part, it's about to add in some noisy. This is original data set. And the right plot is to add some noisy. The noisy is a blue dot. Okay. So now we will optimize our linear regression model based on different loss function, L2 and L1. We will think which ones can return a better linear regression model with this adding noisy. Okay, the robustness of the L2. For this one, we use the L2 loss function. Okay, we will compute the gradient and use the gradient descent to optimize our loss. Our loss is L2. Okay, and do the optimization with different iteration. Like we have multiple iteration steps and many iteration steps, and this is our final estimation about like the beta one and beta, like the beta 0 and beta 1, and we can get the mean square error to measure the performance of our estimate linear regression model. And for the second, we use the L1, like the absolute loss function. Okay. For this one, used in the linear regression model, we can use another, like the mathematical approach to calculate the gradient, because this is L1 now. So the gradient is different than the L2. Okay. For this one, we use the L1 loss, and we also do the same things as in the L2. We do optimization and with a different iteration. Okay. And we will given our final result and return to the mean square error to measure the performance about the L2. Okay, now we make a summary about the L2 and L1 loss. Because in our data, we add some noisy, and we want to, this noisy do not affect our model training. So we use L2 and L1 loss function and train the model. We can see the use mean square error measurement. The L2 is better than the L1. We can say like the blue line is from the L1, the red line is from the L2, and we can say the blue line is better to fit our training data. Okay, this means like the L1 norm is more robust to the outliers, like this blue dot. Okay, so now I have introduced all the things about the today's online tutorial, and we will go back to the online tutorial X. So I will make a summary about today's online tutorial. This we have three things. One is about to understanding the maximum likelihood function with two intuition examples. Okay, one is just a simple case about the weight object, and the second is about linear regression. And the second point about today's online tutorial is to explain why we assume the y's following a normal distribution for because we make the assumption on the epsilon is following Gaussian distribution, so we assume the y's also from normal distribution. Because in the ground truth scenario, these things happen, so we can make this assumption. Okay, and the second is we explain the robustness about the surrogate loss function. This actually measures the change ratio based on a different residual and a different loss function. Okay, and we also use some coding, like a coding about the maximum likelihood and a coding about the robustness. Okay, now for someone have questions, you can make a question now, and I can accept any question you want to ask. Okay, for someone ask question about the Cauchy loss and the core entropy loss. Okay, firstly, for these two laws, they have a score parameters. This parameter is like some parameters. Okay, you can define this parameter before you use this loss function. Okay, so the robustness is do not have any relationship between these scale parameters. Okay. And what the difference between the Cauchy loss and the core entropy loss? Actually, for this loss function, there are different loss function and from different distribution. And the loss function is look different. I can show you the function loss. And, yeah, for someone, if you want to ask a question, you can unmute yourself and make a question. one is a controllable robustness, and the other method robustness related to the variance of the error. Uh,艾伯西can unmute yourself, or because I do not very understand your question.
I'm in
Hi,
the library now. So maybe there are some noises.
what's your question?
I just want to know um what's the difference between the class zeros and the current tropic loss. Um, I I guess one is the one of them is to be controlled and the others is dependent on the uh, variance of the error. I guess I don't know. Is it right? Because in the currency loss, we can find there is a gamma parameter, and if we control this, we can get a
Uh,
smaller
uh,
or bigger coefficients and change the robust.
yeah. For the current entropy loss, they have another scale parameter is like a sigma. Actually, sigma and gamma can be same. It just have different donation.
can
This is also like
can
a
be
scale parameters. This scale parameter is like the hyperparameter in your loss. So you can define this parameter like this parameter equal to 1 or equal to 2 in this loss, in this two loss. And actually, this two loss function is totally different. They have different definition from different distribution, and they have different shape. I can give you,
but it looks like they when we uh when we increase the R, the residual, and
yeah,
the robustness will
the robustness is
decrease.
different. Robustness, no,
Uh,
no, we cannot say like the robustness is decreased because robustness is just a character. Okay, we can say the robustness is well or bad. Okay, so for this one, we take a differential with respect to r is like to, we want to find the change ratio. If our r increase, what is the change ratio about the actual loss value? Because the deviation can give us this information, right? So like if the r changes the 1 unit of loss value, maybe it can change to the change ratio multiple the 1 unit r. It's clear?
okay, so maybe the other questions in the least squares, least
Yeah.
squared, um, why we have to assume the errors, the distribution of error is normal distribution.
Okay, you mean why we need to make a normal distribution assumption
Yes,
in linear regression? Uh,
yeah,
Actually, for this assumption, we can make an assumption like the normal distribution or Laplace distribution or Cauchy distribution. We can all make this distribution. But in statistics theory, we think in a real world, the normal distribution is like the more popular distribution. They are like
yes,
yeah,
yeah, I know the normal distribution is the more popular, but
yeah.
um, is it necessary for the linear regressions to assume the distribution of errors is normal distribution?
Uh, because we think the normal distribution is more popular and can be widely accepted. So normally we can think our linear regression and our epsilon is belong to the normal distribution. But you also can choose this epsilon is from the Laplace distribution or
Okay.
Cauchy distribution. Yeah.
Okay.
If
Yeah, same.
if you think the epsilon actually is from you can make this assumption. So important things we want to cover is like if you make an assumption about your epsilon is belong to a normal distribution, you can also make a assumption like the y is also belong to a normal distribution. Because in the ground truth situation, these two things should have the same distribution. So this is like the important things we want to introduce.
Okay, but in
Yeah.
the least square laws, um,
Yeah. Yeah, this square loss.
yes, least square laws, oh, not this one, not this part. Maybe go up.
Square loss.
Um,
Yeah.
oh no, not this, not this. Go up, not go down, go outside. Up, up. Not here. Still up. Um, okay. Um, maybe could I show the screenshot?
Yeah, you can share screen.
Um, oh no, not my. Could I just put this the in the chat platform? This is the screenshot of
Okay,
our
okay. I
slide in
see.
the lecture.
I can show
I
you.
yes.
Yeah, yeah. We can.
But
I can show you this. Oh, yeah. Uh,
um, in these tools in these two screenshots we can get the W and C
yeah,
without
yeah.
the noise no without the
Can
errors.
can.
So why we have to assume uh assume distribution of error?
Okay, I got your point. Can you see this? Can you see this screen I sharing? Okay, you
Yes,
can.
I see, I
Yeah,
see.
yeah. For this case, actually, you can direct because you say in this case you use a less square loss, right? In
Yes,
the in this formula. So
yes,
so why you can get this result? Because you use a less square loss to do the calculation. This is right.
yeah,
So you use a less square loss. This is like the assumption in this formula, correct?
yeah,
Because if you use absolute loss, maybe your gradient is different. Maybe your W is different, correct? Because this derivation with respect to W is belong is the reason is like the less square. You use the less square loss and use less square loss to take a derivation, correct? And for this case, why you can directly get the W value because you think you know in the in this in this loss the minimum value is from the global minimum point. In the global minimum point, the gradient is equal to 0, correct? So you can directly calculate what is y exactly, correct?
yes,
Yeah. But we can say in the linear regression optimization, if we make a assumption about the like the normal distribution. I can show you. Yeah, show you. Let's show the text. We can say in our linear regression model, this is also a linear regression model. In our linear regression, we also make assumption like the equivalent is from the normal distribution, correct? And the y is also from normal distribution. And for this case, we use
But
normal distribution probability density function. And we want to maximize our local likelihood function, correct? And the maximum about this local likelihood function is like to minimize the last square loss, correct?
yeah,
So this is like because in your case, why you can directly calculate W because you think you got the global minimum point and you think in the global minimum point greater than or equal to 0. So you also do another optimization process. And in this process, you falsely assume you use less square loss and direct give the result. And for this case, you falsely assume the normal distribution. And the final result is also a least square loss. So actually, these two things is the same.
they are the same. Okay.
Because if you make assumption like the normal distribution, you use a mathematical proof, the final result is like the minimize the last square loss. And in your case, you also use the last square loss to measure difference, and the result is like the W equal to a one calculation function, correct? And why we can make this calculation function? Because we think in the minimum point, the greater than equal to 0. So these two things actually is the same thing.
Okay.
Yeah,
Yes. Thank you.
yeah. Because if we think this is equal to 0, we belong to our minimum point. And in your case, you use the last square loss and found the minimum loss. And the gradient is equal to 0. So this like you falsely use the last square loss and to calculate the direct calculation function about the W and C. For this case, we make a normal distribution about the Y and to go through the mathematic process, and the final result is also a optimization about less square. So these two actually is the same thing. Okay, hope I have already answered your question. Okay, and for other guys, do you have question? Feel free to unmute yourself and ask me. Okay, I will wait around 10 minutes. If you have any question, feel free to propose.